Okay, to answer the question of how to transform a function, an exponential function, I have graphed f of x equals 3 to the x power, an exponential function. And you'll notice when x is 0, y is 1. When x is 1, y is 3. When x is negative 1, y would be 1/3, because 3 to the negative 1 is 1/3. When x is 2, y is 9, and you get the idea. Now I'm going to start with g of x here, and what I've done with g of x is I've taken every y value that was 3 to the x power, and I've just multiplied it by 2. So this 1 would be multiplied by 2 and become 2. This 3 would be multiplied by 2 and become 6. 1/3 would be multiplied by 2 and become 2/3. And so what it will look like here is a stretch of the original function. Now, if I modify that function and make it negative, then what that does is it simply changes that stretch to be in a different direction. And we scroll down a little bit and take a look. And now it's a reflected value of that, not just stretched, but also reflected. And so a y-axis reflection is created by a negative value there. And if I modify it again, we'll put it back to positive and put 1/2 instead of 2. Instead of a stretch now, all those values being cut in half, 1/3 goes to 1/6, 1 goes to 1/2, 3 goes to 1.5, and so on. I have kind of squished it down or shrunk those values. Okay, and so I'm going to go ahead and remove the graph of that so we can focus on h of x. And what I've done with h of x is I have just taken all those y values, which were created by 3 to the x power, and I've added 4 to them. And so that will change 1 to become 5. That will change 1/3 to become 4 1/3. That will change 3 to become 7, and so on. And so I go ahead and plot this function, and there we go. One thing that you'll notice is on the previous function, remember we had our asymptote at y equals 0. And that happened because as x got really, really small, we're dividing by 3 a large number of times, and that gets us a value that is really, really close to 0. Well, now you add 4 to that, what we'll get is instead of an asymptote at 0, it's an asymptote at 4. We get really, really close to 4 as we get small values of x, and yet y can't get smaller than that 4 because I can't make this become a negative value. Okay, and so again, let's go ahead and remove that. Now we can focus on the function q of x. In modifying f of x to make q of x, what we did is we just added 1 to the exponent of x. And so now 3 to the 0 plus 1 when x is 0, I'll get 3 to the first, or 3. And when x is now 1, 3 to the 1 plus 1, that's 3 to the second, and so that would become 9. And 3 to the negative 1 plus 1, that'd be 3 to the 0, and I would get 1 right here. To get 1/3, I would have had to put negative 2 in. And what we've done with this one, as you'll see when I plot it, is in some ways we've changed the amount vertically, but really it's been changed horizontally more, because when I had a negative 1 for x, I got the same result as before when I had a 0 for x. When I had a 0 for x now, I got the same value as what I did before when x was 1. And that can hold true. You'll notice that it doesn't really appear to make much of a difference when it's down here, because 3 to a negative, really large negative number plus 1 is still pretty negative, and 3 to a very negative value is pretty much 0. Doesn't matter if you add 1 to it or not, it's still pretty much 0. Okay, and that difference seems to be quite a bit larger as I go up here. Then finally, r of x, what I've done to modify that is I made the x value negative, and that's kind of a curious thing. To make the x value negative, it seems to have really changed some things here. Now, when x was 0, I had no change. negative 0 is still 0, so that kind of makes sense. When x is negative 1, negative of negative 1, well, that's 1. 3 to the first is 3. And so I've gotten the opposite thing. Whenever I had a positive value before, that's now the value that I get when x is the negative version of that value. And so this is a y-axis reflection. So a stretch or a shrink and a y-axis reflection is based on changing a multiplicative value in front of that. A vertical shift would be adding or perhaps subtracting a value to the 3 to the x power. A horizontal shift would be adding or subtracting based on x, the exponent itself. And a reflection on the y-axis, or across the y-axis, would be making the x value negative in the exponent. So we've learned before that a function and its inverse graphically is represented by a reflection across the line y equals x, and that's because you switch the x and the y as part of finding the inverse. Well, we know and we've researched to find that the logarithm is the inverse of taking x and putting it in the exponent position. So f of x being 10 to the x power, the inverse of that would be g of x being the log base 10. Remember, if the base is not written, that's implied to be a base 10 logarithm. So log base 10 of x is the inverse of 10 to the x power. And checking to see that it is indeed a reflection across the line y equals x, well, I have the point 0, 1, and in the inverse it's now 1, 0. I have the point 1, 10. In the inverse, I have the point 10, 1. We have the point negative 1 comma 1/10, and then in the inverse that would be 1/10 comma negative 1, and that does seem to fit. Now this program seems to have stopped the line right here. In reality, it does infinitely continue, and it has a vertical asymptote at y equals 0. It does end up getting infinitely large. It just takes infinitely long to get there. And that's kind of a weird thing to look at too. All right, so it does work that the log is a reflection across y equals x of the original power. And we can see that even if we change the base, although I won't take the time right now to do so. Okay, so hopefully you're beginning to see the pattern here. And again, I've graphed f of x being log of x. And remember that base 10 is implied in there. And seeing the pattern, now we've added 4 outside or after that function. That should just do a vertical shift. We've added 3 here. I'm betting that's a horizontal shift. I'm betting it's opposite of that 3. And then we've multiplied a value on top. I'm betting that that's a stretch. So let's go ahead and check. I'm going to plot the function here. And yes, indeed, it did shift over 3 from where it was. It shifted in the opposite direction, so left instead of right. And if I modified this function to, instead of be plus 3, let's say it was minus 2, then, yep, I shifted right too. So my prediction was correct for this one. Plotting over here, we plot the function. I'm betting it goes up 4, and it went from there to there. Yep, from 1, 0 to 1, 4, and indeed it seems to have followed that pattern. And if I modify this and say minus 5, it should go down 5 from the original parent function, and indeed it does seem to have done that. So my prediction was right on this as well. And then finally, this one I'm going to predict to be a stretch of that, because I'll take those y values and double them. And so I'm going to go ahead and plot those. And indeed, it has taken what I had here at 10 comma 1 and made it 10 comma 2. 0 doubled is still 0. Now, what was at looking to be, some 1/10 value comma -1 is now 1/10 comma -2. And so it has kind of stretched that value, although it's a little bit funky and kind of looking at that. And if I made it 0.5, then it's kind of squished it in closer to that x-axis. And you see that right there. So my predictions do indeed turn out to be right. And of course, if I made this value a -1, it would reflect it across the axis, across that x-axis there, just like I predicted. And if I made x negative in here, it would reflect it across the y-axis. This is following the patterns that we've seen before with all of our other functions. And now, by way of summarizing, I'm going to take an equation, not in function form here, but an equation y equals b to the x power. No matter what b is, if I transform it and I put an a on there, and I do x minus h in the exponent and I add k, that's doing some transformations. Here's a sketch of that original parent function. I picked some random coordinate h comma k. It looks like k would be a positive value of some sort here, and h would be a negative value of some sort here. But if we do that, the a value stretches or shrinks the original function and perhaps reflects it across the x-axis if a were a negative. The h translates it horizontally. It goes in the opposite direction of h, so an x plus 2 in that exponent would go to the left, and you get the idea. And then the k value translates it vertically, as we've seen many times before. And so the function now, after that transformation, it would have picked up and moved. The asymptote would now be at k, not at 0. The stretch would have created so that the distance between the coordinate h comma k is the a value, rather than right here the distance is 1. And then just from there we kind of plot our points and continue moving on. Let's talk about the transformations on log base b of x, no matter what that base is. As you see, the a value multiplied in front of it will create a stretch or shrink across, and if a is negative, it will reflect it across the x-axis. An h value translates it horizontally, so it goes in the opposite direction. So, like as I said before, an x plus 2 would go to the left, and translates vertically with a plus k at the end of that. And so we could see, given our coordinates h comma k, if we were to plot that, the vertical asymptote that was at x equals 0 is now at x equals k. The distance from 0, 0 to 1, 0 on the logarithmic function is maintained. It's just now from h comma k to whatever h plus 1 comma k is, and that creates a point. All those other points are shifted over just like before, and then we just would have seen some multiplicative stretch based on a as well. All right, hope you find this helpful, and good luck graphing your logarithmic and exponential functions.